My name is Alyssa Ramsey, and today I'm going to talk a little bit about what I've learned about neural networks. I've always been sort of curious about neural networks, but I never really understood how they worked. And the reason why I'm curious about them, and I'm sure you guys know as well, is that neural networks do lots of things, everyday things that we come in contact with. For example, neural networks help keep spam out of our email boxes. They're used to find certain images on the web or keep us from finding certain images. They're also used in machine translation, or they're being used more and more with translation. So for those reasons, I was interested in neural networks, but the thing is, I wasn't sure if I could really understand sort of what a neural network even looked like or how it operated, since I don't have a very strong math background. But I sort of dove into it anyway and found that you can actually sort of get an idea of how it works anyway. You can understand what it means to train a neural network without knowing exactly what all those little functions do. So today, since I wasn't able to find a video or a TED Talk that really sort of was in between the very sort of superficial talk about a neural network and also the very, very technical, that's where I'm sort of hoping to be with this presentation. So what does a neural network look like? What's its basic structure? At its most basic, a neural network is comprised of 3 layers, and each layer contains neurons. So we can see right here, this first layer, the input layer, has 2, hidden layer has 3. Normally, the hidden layer just contains some amount of neurons between the input and the output layer's number of neurons. And then here we have an output of 1, and again, the input, or the number of neurons within an input or an output depend on what you're doing. We'll see a little bit later, we'll work with an XOR function, or we'll make this network mimic what an XOR function does. So that's why we set this one up this way. And then we have a neuron. But what's a neuron? Like, how does it even work? How does it pass information from one to another? What does it do? Well, you probably have the sense that it's something that contains a value of some sort. And this, I'll refer to that value a little further on as either its final value or its activation. Those all sort of mean the same thing. That is the value that is passed from one neuron to the next. Obviously, if it's in the input layer, like we have over here, the activation value of the neuron is assigned. It comes in from whatever data you're having your neural network read. And another thing it can do, a neuron can do, it can connect to other neurons, and each connection is assigned a weight. So you can see here we have this input layer, 1 neuron, and then connections to these 2 neurons, one with a weight of 0.3, another with a weight of 0.8. You might be wondering, like, what are these weights? How do you decide on what number goes there? Basically, it's a float, and the numbers are random. And the reason why they're random is because when you go through the training process, these numbers are what are gradually adjusted to get the network to do what you want it to do. But we'll get there soon. So here's sort of a very basic, hope by now that you have a pretty basic idea of what neurons are and how they connect to each other. But there's one more thing that each neuron does. And this is where it gets a little bit complicated, but still nothing too intense, I think. If I can handle it, you guys can handle it. So what each neuron does is that it can calculate its activation by going through 2 steps. So the first step is that it sums up the input value times the weight for each connected node. So what does that mean? Well, let's figure out what this one's input value would be. So we look at node 1 over here and its weight. So what would be one of the numbers that we're summing up here for its initial value? So if this value is 1 times 0.3, 1 times 0.3 is 0.3. OK, and then we do the same for whatever other neurons are connected to it. So what would be the initial value here? We have 0.3 and 0.6. Yeah, 0.9, right. So that was pretty easy, right? So that's basically the sum, or the initial sum of this neuron. And then we do the same thing for the next one. And basically any other neurons in what would be a hidden layer, or a following layer. There we go, we got that. There are sums. Okay, here's where it gets a little tricky, but still nothing too intense. What we do is that we put this sum through something called a squashing function, or an activation function. And what is that? That's a bunch of fancy math that basically turns this value into a float. It turns it into a value between 0 and 1. And why do we do this? What's the point in doing this? Well, basically, it's what allows the neural network to deal with nonlinear data. And we'll talk a little bit more about what's linear and nonlinear data later. But so just for now, know that this is where the fancy math happens, one step. So if anyone wants to guess what the activation of these are, you could go ahead. But it's basically done with this function here, where t is equal to the hidden weight. So that's basically it in terms of how neural networks pass on values. And even if we don't have the answer here, what we're left with is this is basically what this neuron's activation would be, which means this is a value that would be passed on to the neurons after it. Does that make enough sense? OK, so that's all to keep in mind, is each neuron has hidden values, or sorry, each neuron has, each neuron has its sum, which is made up of the values that are coming in from other neurons and their weights, and then is put through a squashing function, which gives you its activation. OK, so another thing that I was really curious about is how do you train a network? Like, we're not talking about a puppy or a person. Like, how can a computer be trained? Just by changing some numbers around. So I will quickly walk us through an example of how a neural network is trained to mimic an XOR function. So everybody is familiar with how an XOR function works, right? So the XOR function, basically, only when the two inputs are different, we want like, for example, when the two inputs are the same, we only want, it's not true, basically. So here we have basically an entire neural network set up that can be trained to deal with, or to mimic the behavior of an XOR. So we have our initial weights, which are arbitrarily assigned. And then same with these. And we have our initial values. So right now, we're just going to be testing the first case, where the inputs are 1 and 1. And what do we expect to be our output, then? If it's 0, right. And a good question might be, well, why bother trying to mimic an XOR function? Because it's pretty simple, and obviously we have a function that does it perfectly already. And the reason why we do it is because when the first neural network was put together, a neural network machine was put together about in the 50s or so, it couldn't deal with, or it wasn't capable of mimicking an XOR function. And that's because there's really no way to split up the data in a linear way. Like, for example, usually you would want data to be like, OK, so here's the X's, here's the O's, we can draw a line. With XOR, we can't do that. We need 2 lines. So that's why the original, it was called the perceptron neural network. So neural network wasn't able to do an XOR. But now, because we use some calculus, it can. So here we're going to go through, like I said before, take the input values and the weights and get their initial, the sum. And then after that, put it through the squashing function to get the value that's then going to be passed on to the next neuron. So, so the values that are going to be passed into the output here are 0.73 times the weight. That goes here, and we do that for each one. In the end, this is the overall sum. And then the overall activation, or the output, is the squashing function, what comes out of the squashing function of that. And it's 0.77. So basically that's how data travels through a neural network. We're all the way through, we got to the end, and this is our output, which is great. But it's pretty far from what we wanted, right? Because we wanted 0. So what do we do about that? How do we get our network to learn, to correct itself, basically? We use something called backpropagation, which is basically you take the error that comes from from the activation at the very end, or the output, and then you feed that error back through the system so that each of the weights are corrected just incrementally. So in order to get the margin of error, it's pretty easy. You take what you wanted, 0, and you minus what you got. So our margin of error is negative 0.77. And then there's some more fancy math. This time, instead of using an activation function, before we were using something called the logistic sigmoid. Now we use its derivative. So that's why we got an S with a little comma. And we apply that to the neuron's output sum. So this number, before the activation was applied, that's the number that we throw in here and squash it, and then times it by the margin of error. So what does that give us? It gives us this. And what we do with this number is figure out It helps us figure out how we should change the weights that feed into this neuron. So here, we're trying to figure out how should we adjust this weight so that it brings more accurate number, or something closer to what we're looking for, into that output neuron. So by doing that math, we get the number that we need to change the weight by, and then we minus that number from the weight, and then we get the new weight. So the new weight was 0.2. The old one was 0.3. So as you can see, the value of the weight is decreasing, and eventually what's going to come out of this is a smaller number. And we basically do that for each neuron. Just take a little bit, basically shave a little bit off the weight of each connection. Okay, so now we got our new weights for that layer, and we need to move on and do something pretty similar for the next. Because we can see all of them are now smaller. And there's more fancy math involved in the next step, but there's just maybe one extra step or so. Again, taking the derivative of, this is the derivative of the squashing function, and taking the original sum that came in from here and here, and then multiplying it by the original weight that came after. And then we get the number that we want to adjust the following weight by. And that number is also multiplied by the input. In this case, it's 1, so it's the same. So we take 0.8 minus 0.008 and do the same for the other weighted input. And then we get our new weights, which, again, they're smaller. We're looking for a smaller number. So good. Then we do that for each and every single one. And basically now, when we run the test again, and we give it inputs of 1 and 1, the number that comes out should be smaller. It should be closer to what we want. And this is how it works. You basically just slowly adjust the weights in the system to get the proper output. And we could see those were the old weights. And so I'm not sure how much time I have left here, but some resources that are really great for if you were interested in neural networks and even kind of trying one out, possibly. There are some node libraries that allow you to mess around with a neural network. And I can show you one of them really quick and do basically what we just did with a diagram. So here we've got, is called a perceptron, or as you can see, it's in a library called Synaptic. You can just look for it on GitHub. And you take out some of the sort of important, or the building blocks of a neural network. So you need neurons, you need layers. You can use a network. Sometimes you can just use layers. And also a thing called a trainer, which is basically the function that feeds information into the network and also makes it do the back propagation to get the weights corrected. All right. And here we can see this is our little neural network. And like the example, there's just 3 layers: an input layer, a hidden layer, and an output layer. And the project function is basically saying, OK, there's a connection here between the input layer and the input layer and the hidden layer, and then the hidden layer to the output layer. And then after that, and then there's the trainer. So this is how it, at least in this library, how a training set is set up. You say what the inputs are, what the outputs are, and then you tell it the learning rate, which that's something that there doesn't seem to be any exact science in terms of what number to assign to it, but it's basically a number between 0 and 1. If it's lower, that makes it learn a little bit slower. If you make the number too big, it will possibly cause your neural network to overcorrect. So you kind of try to find something in between the two that works well. Then you can also say how many iterations you want to run of the training set, the error you're going to accept. So once we get to 0.005, we'll say, OK, yeah, you can basically do an XOR. And then shuffle. There's different, what would you say, different options and stuff. But a very useful one is log there, which basically outputs to the console well, I guess you'll see in a second. And so here is where we're outside the trainer, and we're just saying, OK, use this data, and we'll see how it does. We'll see what its output is. So where do we run this? We actually can run this in the browser using something called Browserify. You just have to install it. And what we get is, and it disappeared. Sorry. OK, what we get is something that looks like this. What's really neat about it is that every time you reload your HTML, it actually reruns the training, and you see your outputs. So here are the 4 outputs, like the first case, second case, third case, fourth case. So inputs 1, 1, 1, 0, 0, 1, 0, 0. And you can see, as you run it, so after 1,000 iterations, it already did it. This shows the error. And you can actually see how the error decreases after a certain number of iterations. You can see up here it's kind of small, but here it's at 0.725. By the time it goes through 7,000 iterations, it's hit sort of the cutoff point where we say, OK, you can do an XOR. And it did, pretty much. When we feed in, 1, 1, it gives us 0.058. So it's pretty close. When we feed it 0, 1, it gives 9.95. And so on and so forth. And the neat thing is that it's really actually doing it right now. This isn't a function. It's really, every time you reload, it's relearning and giving slightly different answers. Sometimes the iterations will be less. But yeah, it's a real neural network, and you can actually see how it works, and you can mess around with it. So yeah, I guess that's what I hope to impart upon you guys today. There's more than one neural network out there. I liked this one the most. I think it was the clearest. The synaptic one, there's also one called Mind. And yeah, if anyone has any questions about synaptic, I can't say it, synaptic or Mind, or using one of the two with Browserify to get it running in the browser, I'm here. All right, thank you.